Well, we kind of assumed this in the n anyway. So suppose p divides some positive integer n, p is a prime at least 5, which is useful here somewhat. So we constructed a map var pi from the homology of x1 of n. And I did z1 over 2 coefficients last time, but this time I'm going to just take zp coefficients, mod I. And then it went to k2, which by the theorem of Tate last time was the homology of the maximal unramified outside p extension of mu n, q mu n, and then the plus part of both these things. So here this was Eisenstein ideal in a Hecke algebra. So it was generated by Hecke operators TL minus 1 minus L, diamond operator L for L not dividing n prime, and UL minus 1 for L dividing n. OK, so this, yeah, now I just, OK, so the idea here was that, OK, so this thing sent a Monin symbol. It was very explicit to a Steinberg symbol. And somehow this was part of the philosophy that geometry of GL2 over Q tells you something about the arithmetic of GL1. Now, in fact, I mean, as I explained last time, this thing is closely related to the class group of Q mu n, and at least mod p. And so in a sense, I mean, and exactly if, say, n were a power of p, this object and somehow is, well, not exactly, but this object somehow is giving you some sort of explicit presentation of the p part of the class group, or the p part of K2. If you believe that, if you believe that this map is an isomorphism, which was the conjecture. So in this talk, I want to construct a map in the opposite direction. Call it Epsilon. So that's from H2 to the homology of the Eisenstein ideal. So let me give these things names, the names I gave them last time. So this thing was Y, and this group here is S. So this is S mod IS. So I want to construct a map like that. And this map will not be explicit. It's going to be constructed out of the action of the absolute Galois group of Q on the tau cohomology of the modular curve x1 of n over Q bar with ZP1 coefficients. OK, so mod the Eisenstein ideal. So this is going to be the direction arithmetic goes to geometry. I said near the boundary, or you could say mod the Eisenstein ideal. OK, so great. So let me just recall how you construct very briefly, how you construct the Galois representation attached to a new form of weight 2. So if f is a weight 2 level n, say, new form, so suppose it has a Q expansion like this, one way to, well, we get a Galois representation. We have attached to it a Galois representation. And if you like, you can think of it as in taking values in the, I'll just use the ring of the valuation ring. So OF here is going to be the ring generated over ZP by the values AN, which is a finite. I mean, its fraction field is finite over QP. And the way you construct this is, well, you have a map. Maybe one way is we could consider, you have a map from the Hecke algebra for gamma 1 of n with ZP coefficients to OF, which takes the Hecke operator. So I didn't choose a uniform notation for Hecke operators. So let me just say the nth Hecke operator, I'll write it like this, goes to AN. And this is a ring homomorphism. And so I can declare IF to be the kernel. And then I can, well, look at the object TF, which is the tau cohomology of x1n with ZP1 coefficients. And then I mod out by the action of this ideal of the Hecke algebra, which acts on the tau cohomology group, times, this means times this H1. So this thing is then rank 2 over OF, and that gives us rho F if we choose a basis. So, right. OK, so if it happens that AP is a unit, OK, so p-adic unit, then F is said to be ordinary. And this means something in terms of the Galois representation. So this means that the Galois representation, I mean, well, you could tensor this thing, of course, with QP to get a two-dimensional vector space over KF, the fraction field. So then TF is ordinary. And this means that there's an exact sequence. 0 goes to some rank 1 submodule, goes to some rank 1 quotient of, I suppose, OF GQP modules for some fixed choice of embedding of Q bar. So this is some decomposition group, Q bar and QP bar, if you like, of modules. And where, of course, TF sub quo are rank 1 over OF. Okay. And moreover, I mean, so if we want to think of this, so with respect to the appropriate basis, I mean, this is, in some sense, this is saying that the Galois representation is upper triangular. So, so with respect to the corresponding basis, rho F, in particular restricted to IP is inertia, is going to look like the determinant, which is the cyclotomic character times the Nebentypus 0 star 1. So chi p is the p-adic cyclotomic character, and epsilon is the Nebentypus of F, or the character. OK, so that. OK, so what we have is not this IF. What we have is, oh, the wrong page. What we have is the Eisenstein ideal I. So let me just, right? So this Eisenstein ideal I most naturally lies inside. So did I give a name? Yeah, let me call this thing H. And then we have big H, which is the Hecke algebra acting on, call big M, which is the modular forms of weight 2 and level n with ZP coefficients. So, it has the same, so this is the Eisenstein ideal here. It has the same generators and relations in there. And, right, so this H mod I is sort of canonically isomorphic to ZP delta. I mean, again, by Tn goes to 1 plus L. So delta here is Z mod NZ cross, 1 minus 1. Yeah, so I'm going to do something strange with group elements. Let me just think of the group elements as diamond operators for a moment. I'll introduce that later. OK, and then TL and UL goes to 1. OK, so right. So we have this Eisenstein ideal. But if I think of the image of this Eisenstein ideal, right, this big Hecke algebra surjects onto this little one. And if I think of the image of I in here now, H mod I, as I mentioned last time, is now finite, right? And it's somehow controlled by the p-adic L function. It measures congruences between Eisenstein series of the form e to chi and new forms. Somehow, if we mod out by both I and IF, then at the same time, then we'll get something which is approximately, well, measures the congruence between F and e to chi. So let me explain the idea of how you construct a map Epsilon like this. And this goes back to Ribet, I guess, in his proof of Herbrand's theorem. So the idea is that rho f mod I, OK, looks, well, with our basis that we've already chosen, we might write it as 4 maps, A bar, B bar, C bar, and D bar. And this is going to be now some reducible representation. In fact, B bar times of sigma times C bar of tau turns out to be 0. OK. And we know by this that C bar restricted to the GQP is identically 0. So what happens is that if I take, with the way I've chosen things, the determinant of rho f, which I already wrote down here, the determinant of rho f bar, I guess, inverse, times C bar, this actually becomes a cocycle, a 1 cocycle on GQ. And it has the property that its restriction to, we actually have to go up to potentially quite a large group. So GQ mu n, let's just say p to the infinity, so add in all p power roots of unity, is a homomorphism. But if I work mod p, I actually only need q mu np, for instance, if p doesn't divide n, the way I've written it. OK, its restriction is a homomorphism that is unramified everywhere. OK, and so the idea is somehow that your Galois extension, which is a p extension which is unramified, is somehow giving some p part of the class group. And we descend this back down to the level of this extension descends back down to the level of q mu n, and it has a particular action coming from conjugation here of the Galois group delta here, or the Galois group z mod nz cross q mu n over q, odd action, which is determined by the Nabin typist. So that gives us a quotient of the p part of the class group of Q mu n in the end. OK, so coming from the kernel, sorry, not the kernel image. So that's the idea of what we do here. That's how we construct a piece of this group H2, if you like. But what I want to do is somehow construct, this much more canonically. And I want to construct the entire H2. So now I don't want just a map from some quotient of the class group to some quotient of OF. I want this sort of canonical map. So that's basically what much of the rest of the talk is going to be. So let me try to explain. So let's, by the way, let me know if you have questions. OK, so let me try and signal out some components as in the, so I'm going to keep the conditions of there were some conditions on characters in the original conjecture, and I'm going to keep those here, though they're probably, they seem not necessary for the most part. But I will remove the condition that there was a condition that p didn't, there were no primes which were 1 mod p which divide n, and that's not necessary. So I'll leave it out here. OK, so let's let delta prime be the prime to p part of delta. So if I have a ZB delta module A, and I have a character of delta prime, p-adic character, which is the same as, if you like, an even prime to p order character of z mod n z cross. So it lands in some unramified extension. Then I can construct the theta part of this ZP delta module by taking the tensor product over ZP delta prime with ZP theta, where this is the ring, the ring generated over ZP, or the algebra, by values of theta. OK. And this map, which I'll call theta tilde, is induced by theta, right? OK, so that's, as written, a quotient. I might slip into calling it an eigenspace. It's a quotient of A. But because this group has order prime to p, in fact, A is the direct sum over all GQP conjugacy classes of theta. That means apply an element after applying theta, of these quotients. So this is the GQP conjugacy class. Of course, this depends upon the choice of theta in the conjugacy class. OK. So what I want to do is single out some characters which are allowed. So let's let A prime be the direct sum over, I have to specify which theta, where theta runs over classes such that theta is I guess has conductor divisible by, well, it's prime to p order, so I guess it has conductor n, MP, where m is the p part of n. And theta omega inverse, I'll tell you, yeah, so tell you. Prime to p, thank you. Yeah. Theta omega inverse restricted to, well, OK, so let me think of this theta omega inverse as being a primitive Dirichlet character, and I could apply it to P. And then I want it not to be 1. So it could be 0, but I don't want it to be 1. Viewing as a primitive Dirichlet character. So we can extend it to P. And then the final thing, I guess, so let me just tell you what omega is. Omega is, we think of z mod p z cross as a quotient of z mod n z cross. And then we can inject that by lifting to mu p minus 1 zp. OK. And then the final condition is if m equals 1, then I don't want theta to be 1 or omega squared. OK, so that will be the primed part. That'll.
So what does theta?
Mm-hmm.
What does theta omega inverse mean? How do you evaluate it with P?
Right. So so theta omega inverse is now a character on z mod n z cross,
Yes.
and then I take the unique primitive Dirichlet character of modulus n, right? That extends it. So if the conductor is not divisible by p, then I can evaluate it at p by that extension, and it won't be 0.
And what if the conductor is divisible by P?
Then it's 0.
Oh, then you interpret that as
Yeah.
I see.
Yeah. OK. So great. So now if I have a ZP, so H in particular is a ZP delta module, right? Right. Just on the top of this, I guess. So so H is a ZP delta module. And well, in fact, I was mentioning this earlier. I want to take the strange ZP delta action where the group element for J acts as a diamond operator inverse. It'll be useful later. Actually, the map var pi that I constructed last time is delta equivariant, where J acts as the diamond operator inverse on the left, which is the right here, and the Galois element, which raises roots of unity to their jth power on the right. And so this is useful for making it equivariant. OK, so so if I have an H module, if A were now an H module, then I can decompose it. Well, yeah, so I guess I want the notation to be A sub m. So this will be a direct sum over the same theta. I just put the prime here to indicate the theta, of localization at various maximal ideals of the Hecke algebra, where sort of m theta is the unique maximal ideal of A theta, H of H theta containing the Eisenstein ideal. There's exactly one. And so I can take that Eisenstein part, if you like, of this Hecke module. OK. So it's a that's just a notation for the localization. Yeah. It's a more semi-localization. Yeah. So so this will be what we call the Eisenstein part. OK, of A. Great. OK, so so what is H mod? One might ask, what is this localization mod I exactly that I was writing here? So I guess this is essentially due to Mazur and Wiles. Maybe it's put more explicitly in a more general form in Wiles's paper. And that is that HM mod I is isomorphic to lambda mod xi, where I have to define lambda and xi. So lambda will be zp delta prime part, because we removed all the other eigenspaces. And xi in lambda will give me various p-adic L functions. So if I take chi maps delta to qp bar cross such that, so I need to choose its restriction to be, have be one of the characters with this property. OK. So good in the earlier sense. Then I get a map chi tilde from zp delta to qp bar, and I can apply it to this if you like, this element xi. And this thing should be LP omega squared chi inverse minus 1. OK, so there's a unique element with this property when you apply it to all such characters. And so essentially, this is right. OK, this tells you exactly the structure of this quotient. Right. So in this case, chi tilde maps zp delta to qp bar. Right. So let me just indicate how this is proven. Yeah.
Does this fail without these funny conditions on theta?
Well, there's Euler factors that come in, but you can incorporate that to make it, in the whether you use a primitive character or not a primitive character. So no, it doesn't really fail. Otherwise, it's pretty much true. Yeah.
So I'm just thinking also, why do you need mathematical containing I in this definition of theta?
So it's generated, if you like, it's generated by I, P, and then sort of diamond operators minus, which are in 1 plus P, ZP minus 1, or 1 plus, not ZP. The diamond operator is coming from the P part of the group minus 1. And that's a maximal ideal, and it's the only one that contains. Yeah. If you like, you already see these eigenspaces of H mod I are sort of, right, H mod I is already a local, the eigenspaces of H mod I are already local rings. OK, so, right, so how is this proven? So we could take HM mod I, the big H, and by what we've already said, in fact, it's right there, this thing is going to be lambda. And so what this gives us when we see what happens on HM mod I, well, the point is that what makes this fail to be a ring homomorphism here is the fact that you have constant, potentially you have constant coefficients. When you mod out by the constant coefficient, right? So what is the constant coefficient of E2 chi? that I wrote there, or E2 chi inverse, yeah, so I'll just point this out. Chi this over 2 is the constant coefficient of E2 chi inverse. OK, so when I mod out by that, somehow my Eisenstein series starts to look like a cusp form, and you can make it exactly a cusp form. And so somehow from that, you can see that this becomes a ring homomorphism once I go mod chi. So, and of course, it's surjective, because this is an isomorphism. So the whole trick actually in proving that this is an isomorphism is to prove the injectivity. So the injectivity is what is tricky. And so originally, Mazur-Wiles proved the injectivity as a consequence of their proof of the main conjecture of Iwasawa theory. So, but that seems a little backwards. And so, in fact, Emerton, a long time ago, came up with a trick, at least in level P power level. It makes this sort of not necessary, so can prove directly. And this was extended essentially in the thesis of my student Lafferty to arbitrary level. So let me just explain. Yeah, and I think it's worth explaining because some of the objects we'll need later, or some of the come in here. OK, so I didn't give a notation to the cusp forms. So you notice I need this is a little awful. I need 2 m's and 2 s's, right? So s was modular symbols, the homology. This s is the cusp forms, OK? And this injects into the modular forms, which I already gave a notation to. OK? And there are pairings, right? So H cross S maps to ZP. You can find this in Hida's blue book, if you like. So if I have a Hecke operator and a cusp form, then I can take the coefficient of Q of the Hecke operator applied to the cusp form. And this is a perfect pairing. And this extends. So here I have H, and here I have M, but it doesn't quite work with M. So I need to modify M slightly. So this thing, say, would be these would be modular forms with Q to the n coefficient in ZP for n greater than or equal to 1, and the constant coefficient in QP. If we take that, then this same pairing is also perfect. Now, I guess essentially what Emerton in essence showed is that if theta is not omega squared, then in fact, at least on these Eisenstein parts here, or maybe m theta, no, I think just on theta parts, these are the same. So that's right. But so in our setting, at least, this tells us then that we actually have, well, yeah, we actually have a pairing with m. OK. So now, of course, we have an exact sequence. And it looks like this. lambda here essentially is coming from, over q lambda at least is generated by Eisenstein series. And OK, so we can think of this map as taking the constant term. OK, great. So this thing is split if we tensor with QP, but not over ZP. So if we tensor with QP, it has an obvious sort of splitting, I think. So that is, we have a splitting so essentially on a chi part, if we take quotients for chi, this takes 1 to 1 over the constant coefficient e to chi inverse. So I'll just write it like that. So some equivariant version of this. And so because, of course, this is a splitting, then we get a splitting, say, S. So this gives us also a splitting S of M tensor QP to S tensor QP. OK, and so now we have what's called the congruence module. So the congruence module then, so we could look at the image of M, not tensor QP, under this splitting. And that's going to contain the cusp forms. So we could look at the quotient, S M mod S. That's the congruence module. And from what we've said, this is really just lambda mod C. So now we want to take but we want to get the conclusion that H mod I is lambda mod C. So we'd use these pairings we have. We take the dual. OK, so what is the dual of this sequence? Right? So the dual of this sequence looks like 0 goes to lambda, goes to H, goes to H. And here we have the Eisenstein ideal in here. And here we have the Eisenstein ideal. And so we have H mod I and H mod I. And right, and here we have lambda. OK, so this thing is the dual to T naught. This sends 1 to this Hecke operator T naught I was saying, which takes the constant coefficient. What does it do down here, right? When we work, it takes the constant coefficient of our Eisenstein series. So it goes 1 goes to C. Oops, sorry. Thank you. But maybe I should have said, it would have been more helpful for me to write that this is lambda. Right? So we have, so 1 goes to C here, because that's the constant coefficient of the Eisenstein series, if you like. And so this is lambda mod C. Right? So this gives us the result. So the whole trick is just basically that all the modular forms are integral. OK, so now to construct our map Epsilon, which is going to be some canonical version of the co-cycle that appears in sort of proofs of the main conjecture in the spirit of Maser-Wiles, for instance, more specifically, as found in the work of Ota. And I'm doing everything at finite level, though, so I don't have to do much Iwasawa theory. Want to study, as I was mentioning, this object, which we'll call T. And let me take its ordinary part. There's a idempotent which projects to the ordinary part. So H ord is the is sort of the maximal summand in which UP is invertible. And right, so a direct factor. So take the ordinary part of this T. It gives you Galois representations attached to ordinary forms, for instance. So what properties does it have? Let me list a few. Well, one is that it's ordinary. So as I was saying before, we have an exact sequence. 0 goes to T sub, goes to T, goes to T quo, goes to 0 of H GQP modules. And T sub and T quo are rank 1 over H ord, which means if I tensor with total fraction field, then I get, well, one-dimensional things, well, rank 1 things, I guess. So if I, yeah. But these may not be free. But one of them is free, actually. So that's T sub. I'll explain why in a second. T quo has the property that it has an unramified GQP action in the model we've chosen. OK. I should say we also have, I should add it in here while we're dealing with T. We also have the version for the open curve. So we also have T tilde, which is H1 Y1n right? And it also has an exact sequence. This T sub, so maybe I'll write it this way, is really T sub. The T sub is the same, but the quos are different. Okay, so the submodules are the same, the quotient parts are different. And in fact, maybe that becomes a little more sort of clear if I talk about the second property, which is sort of p-adic Eichler-Shimura. So I guess in the heat-theoretic context, that's due to Ota. We all phrase it as more of in the form of Fukai and Kato. So there's a functor, D. So if I have R, yeah, I guess I can take any compact ZP algebra. Let me take big H. So if I look at unramified H GQP modules, so it's a very simple version of a standard functor in p-adic Hodge theory, then I can map to compact H modules. Right, the category. And what it does is, if you like, D of a module M is you tensor with the Witt vectors of FP bar. I guess you take a completed tensor product. And then you have Frobenius acting here and here. So let's call that phi p. And then you take the part which is fixed by this diagonal Frobenius. OK, so this is a arithmetic Frobenius, I guess. So it turns out that D is, so since we're dealing with unramified modules, you may notice this doesn't actually change the structure as an H module. So in fact, D is canonically, no, sorry, naturally, but not canonically, oh, yeah, yeah. Right. Canonically isomorphic to, yeah, ZP unramified. But not canonically isomorphic to forgetful functor. So in other words, D of M is actually isomorphic to M. But this isomorphism isn't quite canonical. However, it is canonical. And that's easy to see, because then you'll only be acting on the right if we restrict to trivial modules, meaning the action is trivial. OK, so what if I apply this to T quo, which is unramified, as I mentioned? Right.
Sorry, can you just, what
Yeah.
is the difference between natural and canonical isomorphism?
There's a natural transformation,
Okay.
but it's not a canonical natural transformation, is what I mean.
What does that mean?
I mean, there are many choices. You have to make choices in order to define this natural transformation. There's not a unique one. OK, so great. So what is d quo? So this is where the p-adic-Hodge theory comes in. T quo turns out to be isomorphic to S. And that sits inside d t tilde quo, which is isomorphic to M. Ord, I guess, because I took ordinary parts. Ord. OK, so right. So that's the second property. Third is a sort of twisted form of Poincare or Weil duality. Again, in the modular, this is also OTA in a sense. Yeah, OTA. Yeah, so this is done up the towers, which is part of the reason for taking the twist. But so we have a Poincare duality, if you like, gives us t cross t goes to zp minus 1. So I just modify this a little bit. First, we can go to zp delta iota 1. And the iota, I have to, it signifies something about the Galois action. So what does the iota mean? So iota means that say sigma in GQ with sigma of zeta n equals zeta n to the j acts as the inverse of the group element corresponding to j. And the 1, of course, means we act by the p-adic cyclotomic character. So it's twisted by the p-adic cyclotomic character. So j acts as diamond operator j inverse chi p of j, where chi p is the p-adic cyclotomic character. And great. So how do we define this? Right. Oh, I didn't write it down. OK. Yeah. So the pairing is something like this: sum over j in z mod n z cross. And let's see. So might get it wrong, but x cup w j or j inverse w and y, and then group element j, something like this. And the reason, so this is the Akin-Lehner involution here. And the reason for the Akin-Lehner involution is because normally this pairing, if I just did it to ZP1, sorry, not ZP minus 1, because I have one, notice I put one twists in my cohomology groups everywhere. OK, so normally the action of an adjoint Hecke operator here, the adjoint action will correspond to the usual action here. I want all my Hecke operators to actually act by the adjoint action. So that's sort of implicit. So that the action is of the usual Hecke algebra through the adjoint operator. But the nice thing about this definition is that it now respects the Hecke action like this. And also, the reason for writing this is because this is a GQ equivariant pairing. Yeah, usual, yeah, Poincare pairing. To H2, right? Yeah. OK, so those are the three properties that T has that are useful. OK. So now let me state the theorem which allows us to construct epsilon. So the construction of epsilon is due to me, and I'm rewriting it a little differently. So as in some of the preprint of Fukai and Kato. So there's an exact sequence. Zero goes to, oh, I need to define something. OK, so so we want to study what? T, which is the T mod IT. But so that we only look at the theta parts that I want, I'll put the M there. OK, so T is the quotient mod I. And I told you it's this Galois action, which is going to give us the cocycle we want. So here the point is that we have an exact sequence. Zero goes to T plus, goes to T, goes to T minus. I should say we have a complex conjugation fixed here all the way along. In fact, we can just think of Q bar as sitting inside C. So here I really mean under complex conjugation, right, the plus and minus parts. Zeta n is e to the 2 pi I over n if I have an nth root of unity. So OK, so we have an exact sequence. But the interesting thing is this is an exact sequence of H GQ modules. So it's actually Galois. The maps are maps of Galois modules. What properties do T plus and T minus have? T plus is isomorphic, if you like, to well, the modular symbols mod I, which we're interested in, and it has trivial GQ action. It's fixed by GQ, every element. And T minus is isomorphic to lambda mod C iota 1 in the same notation as before. And this is a canonical isomorphism. These are both canonical isomorphisms, meaning that this is a free rank 1 H mod I module, or HM mod I module, and it has a canonical generator. OK, so that's useful. And moreover, the sequence is locally split, or even canonically, locally split at all L dividing n. And the fact that it's split at primes not equal to p falls out really quite easily. It's really p where you have to worry, especially because of the assumptions I made of primitivity of the character. It falls out immediately that the sequence is locally split at other primes. OK, so how does this give us what we want? So when we have an exact sequence like this, we get a cocycle, right? A 1 cocycle attached to the coming from the action on T, sort of sigma minus, yeah. You take an element here, right? You apply sigma inverse to it. You lift it. You apply sigma to that. And then you subtract off the original element. That gives you a 1 cocycle. From T minus to T plus. It's an H modular homomorphism. And now the point is that this T minus has a canonical generator. So we can evaluate at the generator. And so we go to T plus. OK, and that's the cocycle that we want. in other words, when we restrict somehow, and that's the tricky part here, when we somehow restrict and go back down, eventually that's why Iwasawa theory is useful, because you don't need to do that, but you get a map from y to, or y prime to Sm mod I Sm. And this would be our map, Epsilon. But let me explain this in a little more fancy way. Yeah.
We called S before. We'd already modded out by the Eisenstein.
No.
H.
I think I wrote S mod IS on the first board.
Maybe I'm mistaken.
Yeah, no, S is a homology of x1n plus with ZP coefficients. Homology H1. Yeah.
No, sorry, I didn't catch it. What was this Epsilon map? Can you say it again?
Yeah, Epsilon is somehow, it's essentially this cocycle. OK? So, but somehow I have to restrict this to q mu n p to the infinity or something where it becomes a character. And then somehow that, yeah. So it becomes an unramified. So this is unramified, right? Once I, yeah. So I'll explain this. Yeah, I'll explain it. OK, I can explain it now. So I restrict it to g q mu n p to the infinity. But now it factors through x infinity, where x infinity is the Galois group of the maximal unramified abelian Pro-P extension of q mu n p infinity. And that's because this sequence is locally split at p. And this is a homomorphism now. But this is big, right? It has some characteristic ideal, which is non-trivial as a modular over the Iwasawa algebra. And this is small. So, so then the trick is that this map somehow is not, it's not lambda equivariant as I've written it in any sense for the Galois action here and diamond inverse operator action here. I think I mentioned this in the last talk. It becomes equivariant when we twist by 1. So we get a map like this, and then somehow sigma j, now I have to extend sigma j to acting on np to the r, I guess, for any r by jth power. Then the action of sigma j here corresponds to the action of diamond operator j, I guess if I call this epsilon, x here. But this is really not quite the map epsilon I want, right? Because it's not from the right group. I need to descend back down to y. And the point is here that x infinity 1 is actually isomorphic to, in the prime part, the limit.
Sorry, I got lost.
Yeah.
I seem to have a map from x infinity to t plus, and now I've got one from x infinity 1 to t plus 1.
Oh, yeah. So yes. So x infinity and x infinity 1 are isomorphic as groups. And the isomorphism is canonical because I fixed a complex conjugation all the way along. So in other words, I have a generator of the Tate module, which I fixed because I consider q bar inside C. And that is the p power roots of unity. So the sequence zeta p to the r for all r greater than or equal to 1. So in order, I have to identify x infinity and x infinity 1.
Yes.
And then once I do that, this map becomes a map which where the Galois action here corresponds to the inverse diamond operator action here. So I'll write it again here. So the point is that if
Somehow this depends on a choice of compatible sequence of p3.
Right.
Unit.
Yeah, yes. Well, but everything is dependent. OK. So one way to think of it, I actually show in the paper that nothing depends on this choice. But so we might as well think of q bar is inside C. So I fixed that from the beginning. Q bar is the set of algebraic numbers. And once I fix the set of algebraic numbers, then I have in here, I have in here zeta p to the r, which is e to the, or nr, any m, e to the 2 pi I over m. And that gives, for when I take zeta p to the r, for all r, that gives me my compatible sequence. So it's fixed at the beginning.
Okay, but now you're claiming something doesn't depend on the choice of q bar into C. Did you say? I mean.
Yeah, well, I mean, I'm just right now thinking of q bar as a subset of C, so then it really doesn't depend. But yes, in the original paper, what I did was choose an embedding, and then I show everything is independent. Or at least the statement, the map is not independent of the embedding, but the statement of the conjecture that I'll make is independent of the embedding.
The map must depend on.
Yeah, the map does, yeah, in the statement of the conjecture, nothing will depend upon the choice of embedding. Right. Yeah, I'll get to that shortly. Yeah. So right. OK. So but let's suppose I've fixed this. Then I get a map like this, and now this thing, applied to sigma j x is j inverse epsilon of x. OK. That's to make that happen. Now I was yeah. So I'll write this down here. So at least on this prime part, which is all in the plus part, this is the same as the inverse limit over h2 z 1 over n or p either way, mu n p to the r zp2 prime. And this is actually because of the characters I chose. There's always a map. And this is what we call, for later use, this is H2 Iwasawa. This is Iwasawa cohomology. So these are under co-restriction maps, mu n p to the infinity zp2. OK. Now this thing, the key fact here is p is odd. These Galois cohomology groups, these are really cohomology groups. You should think of them Galois cohomology of the maximal and ramified outside p extension of q mu n p to the r. And these have cohomological dimension 2, p cohomological dimension 2. So that means that co-restriction gives you an isomorphism on co-invariance. So in other words, if I take co-invariance to go back down, and we know that, right, we can descend this should descend back down to act through q mu n, then this thing maps surjectively, but its covariance become h2 1 over p mu n zp2. And the point is that this map here, this epsilon that we constructed to sm mod I sm now actually factors through this thing. And that's how you get the epsilon. Right. So you have to go up and then come back down. So this isn't ideal. In the paper, I just did everything at the infinite level, and then you don't have a problem with doing this. But let me let me explain I'll explain after the break maybe a different way of doing this. But for now, let me actually ask what the conjecture is, right? So let me skip ahead to the conjecture.
So this is covariance under what? Covariance for what?
Oh yeah, for gal q mu n p to the infinity over q mu n. So if I take because we're descending from the level of q mu n p infinity to q mu n. So if I take the co-invariance for this group, this becomes an isomorphism. OK. So right. So the conjecture. OK, so the maps. OK, so var pi was defined not just on prime parts, but now I'm just restrict everything to prime parts. So this is a map. Yeah?
So
Right. Yeah, you have to. Let's see if I can. The point is that this map is equivariant for this action, right? So, but this action does factor through z mod nz cross. So that means the sigma j action should factor through z mod nz cross as well. And that means that really it factors through this quotient by the coinvariance. Yeah. So you can put the coinvariance here if you like. OK, so remember that this was a map y prime, if you like, to s. I'll just write prime, mod I s prime. And this thing now, I'll just restrict to prime parts. Right. So these two things should be inverse. So this completely explicit map should be inverse to this thing. And really, this thing is some canonical version, if I go up the p power tower, of the map that's used to prove the main conjecture of Iwasawa theory. Right, so maybe yeah, explain that a bit later. Let me tell you what Fukai and Kato proved. Out of space.
So on the big spit, this
Yeah.
lattice, I mean, T could actually be completely split, right? I mean, this could be some sort of trivial
Right,
thing.
right.
I mean, so when one proves the Moine conjecture, you don't just choose the lattice that's not split.
Right, that's right, right.
So
So
you're actually conjecturing that it's a really nice lattice.
that's right, right. OK, so maybe I should say that. OK, so in the proof of the main conjecture, you construct a cocycle like this using some lattice inside, I guess, T tensor, for instance, the quotient field of the Hecke algebra or something, or the quotient total quotient ring of lambda. But well, I mean, you go up the tower, so OK. So there are different choices of lattices exactly because the Galois representation we're looking at an Eisenstein part, it's reducible. So what Wiles does is for instance, we have T sub and T quo. He fixes T sub and then takes the part that generates, right? The smallest GQ stable lattice that T sub generates inside, right? So by taking that choice, you can still do the exact same construction of a cocycle. But the point is now, because you've taken the smallest such lattice, you've guaranteed that this cocycle is surjective. So you have a map like this. It's not going to anything nice like cusp forms, or modular symbols, mod I. But you have a surjective map to something mod I. And what you can show is that the characteristic ideal of that something on the right-hand side is divisible by xi, or whatever, the p-adic L function. And so what you get is that, therefore, this is a surjective map. The characteristic ideal of the thing on the left is divisible by this p-adic L function. And that is exactly what you need. The main conjecture says that the characteristic ideal is the p-adic L function, and one divisibility is enough. So, so that's sort of the idea. What I've done here is, instead of choosing some sort of extremal lattice, or the smallest one in some sense, I just took the natural one, which is coming from T. And in that way, I construct this very nice map. But I know, for all we know thus far, it could be the zero map. OK? So, right. So what do so in some sense, the conjecture says that T is the extremal lattice. It implies that. OK, so so there's a little contribution here from us, but this is really due to Fukai and Kato in some very slightly weaker form. So if I take var pi and then epsilon and I multiply by some derivative of this xi, then I get xi prime. So this is a map from S mod IS to S mod IS. So what is C prime? So roughly, if I have a character and I apply it to C prime, so this should be some element of lambda. And if I take a character, then it should be LP derivative of the p-adic L function, same character at the same value for all chi. So somehow if this C prime is a unit, then you get that the composition is a unit mod C. Then you get that the composition is 1. Or it has, but yeah. And that actually implies that the, well, I'll say what this implies, but I think maybe.
Do you believe these derivatives are unit?
In all known cases, they are. I actually do. But if this were true, the main conjecture becomes a lot easier. Because the Iwasawa module, well, I mean, what I mean is when I say are they units, first we should look in the Iwasawa algebra, right? And then the question is whether Xi and Xi prime as power series share any common factor or not, right? Whether it's a unit mod Xi. So the question is whether you.
So you want to sort of allow C to be infinite order now?
Yeah, I want to think of it as a power series instead of just thing giving values. If I go up the tower, if I want to do main conjecture. And that I believe that it should, right. They should never share a common factor. There should be no multiple factors of the power series which interpolates the p-adic L function.
Zero should be.
Right, single zeros, yeah. But that's not known, right? It's so if you have that, then you know that the Iwasawa module is pseudo-cyclic, and Iwasawa would have already proved the main conjecture in that setting. So somehow the interesting part of the main conjecture is when this fails, but it's not really, I don't think it ever fails. So,
Can you clarify maybe?
Yeah.
I asked you this question last time for the non-expert.
Right.
You have these conjectures. Is
Right.
it given a simpler proof of the main conjecture? Why? What's the point of it?
No, I think of it more as a refinement of the main conjecture.
What would it give you in terms of L functions that the main conjecture does not give?
Well,
Refinement.
yeah, it's a refinement in the sense that it makes the map that appears in the main conjecture rather explicit.
In terms of application.
Well, yeah. I mean, I can tell you why. Yeah, I mean, there are applications to the structure of Iwasawa modules of Kummer extensions by roots of cyclotomic units. You can say something about the structure of those, or the Galois group of the maximal, say, unramified outside P pro P extension of Q mu P. You can say something about relations in that group because cup products give relations in pro P groups. And that's sort of why I actually started to study it. I should have mentioned that if instead of considering cyclotomic units like 1 minus a root of unity to some power, 1 minus a root of unity to some power, I project, say n is like p. And I project that to some eigenspace for the action of q mu p. So I get some element in some odd eigenspace of the cyclotomic units. And I compare two of those things into some part of H2, which is now just an eigenspace of the class group mod p if I work everything mod p. What I end up with is up to some transcendental factor, which I divide by, right? Some period, the L function of a cusp form over the period at some odd value integer I. So these cup product values are exactly telling you those things mod p. I'm not sure that's, in some sense, that's just a rephrasing, but it is telling you something about L values. And I don't think,
So,
yeah.
to clarify, so
Mm-hmm.
main
Right.
conjectures or things like that might tell you that the
Uh-huh.
orders of the two
Right.
groups between which you've got a map
Right.
are the same,
Right.
not that they're
Yeah.
isomorphic as groups or something. Is that?
Right. So the main conjecture is telling you something about the characteristic ideal of the Iwasawa module. And Maser and Wiles actually do use that to prove something about the orders of eigenspaces of class groups at finite level. But yeah, it doesn't tell you the structure. It just tells you the order.
Known that this map assuming this map epsilon is an isomorphism, wouldn't have told you that that was an isomorphism. That's
Right.
that there was any isomorphism between those two groups.
Right. Yeah. No, that was not.
So it's somehow elucidating
Right.
the group structure of something in K theory in terms of cyclotomic fields. In terms
Right.
of
Right.
modular form.
Right. So you have K groups and H2 of cyclotomic fields and class groups and here this is modular symbols mod I, but actually this is canonically isomorphic to the weight 2 cusp forms mod I as well. So it's saying that the cusp forms are explicitly described by mod I are explicitly described by K groups.
So you want to say that epsilon is isomorphism Fukaya-Kato this I prime?
Well, we don't know that epsilon's an isomorph. Oh, I'll say Ota is now shown, at least he has a preprint that shows that if the restriction for a given character, P doesn't divide phi of n, if the restriction of the character to Z mod PZ cross, I'll write it here, theorem Ota, if P doesn't divide phi of n, and theta restricted to Z mod PZ cross has non-trivial kernel, which if n is 1 is always the case because theta is even, kernel, then epsilon on the theta component is an isomorphism.
So yeah, so because you use this result of Botzel that shows that
Mm-hmm.
this already is the mu max is a mu deprived lattice.
Right, it is a mu deprived lattice, right.
Yeah.
So extremal in the sense that, and there's also results of Wake and Wang-Erickson on this using the theory of pseudo-deformations on epsilon, really. But they're slightly disjoint. I mean, they don't have this restriction in particular, but under some version of some Van der Waals type conjecture, they can show that so if the plus part of the class group of Q mu n is not Wake Wang-Erickson, so if P does not divide the plus part of the class number of Q mu n, then epsilon is an isomorphism. Again, P doesn't divide phi of n, I guess, in what they do.
Converse to that.
Hmm?
If
Con-
Van Dijk's conjecture failed, would
No, this should still be an isomorphism even if Van der Waals conjecture fails. But yeah. And sometimes it does fail because I took Q mu n here and not Q mu p. Yeah. OK, so maybe this is a good time for a break, past time for a break. OK, I wanted to let me just say a few more words about what's been proven before I move to something else. So what do Fukaya and Kato actually prove? They show that if, so Fukaya and Kato show, actually they show a number of different results, but if we have two Hecke algebras and H and big H, right? They show that if these are both Gorenstein, so what does that imply? Implies that the cusp forms are actually, which are dual to the Hecke algebra, are actually isomorphic to the Hecke algebra. And the modular forms are isomorphic to the Hecke algebra. And the p-adic power series interpolating the L functions LP omega squared chi inverse S minus 1, somehow has no multiple zeros, if you like, or no no common factors, no square factors. Then the conjecture holds. So actually, I had already shown that, so this condition was essentially to give that epsilon is an isomorphism. And then this condition, so that's that the big Hecke algebra is Gorenstein. Then this condition of being Gorenstein then somehow gives you the cyclicity of the Iwasawa module you're looking at. Wake and Wang Erickson prove that if P doesn't divide this class number, then both Hecke algebras are Gorenstein. That's really what they prove. So in other words,
But the Poincare theorem you have up there doesn't seem to have this Gorenstein assumption.
No. This is This is not how they show this result. This is an additional result. So I'm more explaining what Wake and Wang Erickson do. So actually, if you have, so in other words, more than this, they prove that Vandiver's conjecture implies the analog of Vandiver's conjecture implies my conjecture.
So then,
Yeah.
if I understand, so what Kato also show
Mm-hmm.
that under this Gorenstein condition, this multiplication by Z and the
Mm-hmm.
this multiplication by like C prime is unnecessary.
No, I'm assuming that p-adic power series has no square factors here. So you still need it. I mean, OK, so what would happen? If HM is Gorenstein, the Iwasawa, little hm, if both are Gorenstein, then the Iwasawa algebra becomes lambda mod something. But that something might still have square factors. Right. So what you get from that alone is then that Epsilon and var pi are isomorphisms, but not necessarily that they're right. That there could be their composite could be multiplication by some number. And in fact, I should say, in the original conjecture, the way it was stated, I didn't conjecture that epsilon and var pi are inverse isomorphisms. I said that their compositions are a canonical unit in the Iwasawa algebra, a canonical unit mod Xi. And I suspected strongly, in fact, in some versions of the preprint, I put that the unit should be 1. And so now I've phrased the conjecture this way. But in some ways, it's still safer to just say that the composite is a canonical unit.
So Wake and Wang Erickson do not prove that these
Uh-huh.
inverse to each other, only that Epsilon is an isomorphism.
Yeah, well, they prove that they're inverse, but that proof goes through the Fukaya-Kato result. What I mean is they prove that, yeah.
Where does the Epsilon being an isomorphism come from in there?
Oh, right. You're right. Yeah, sorry. I see what you're saying. I said the wrong thing. Yeah. So if you combine this with the derivative result, then you get the conjecture, right?
But the derivative result is not an assumption of the Wake-Wang Erickson theorem.
Right. That's right. They don't prove anything about var pi, really. Yeah, I mean, not directly. Their work is all with epsilon.
They prove that Epsilon is an isomorphism by a different method.
Different method of pseudo deformations. They consider some pseudo deformation ring, ordinary pseudo deformation ring. Yeah, R equal T type theorem. And they prove something slightly stronger for pseudo isomorphisms with something weaker, like that the plus part is finite sort of thing. Or they localize at a height 1 prime and prove some weaker result. I mean, one trick here is, I should say, now that we have this as an isomorphism, that's good. But one trick is when you go to the inverse limit, you have this Iwasawa module y on the left, and which is this x infinity twisted by 1. This thing is known to have no p torsion. But in the inverse limit here, this thing may have p torsion. It is not clear that it doesn't have p torsion. And so if you don't have something like this is Gorenstein, then it's not clear that that doesn't have p torsion. And so sometimes you can get the two things are inverse up modulo torsion in this group. But now that we have, I mean, except that there's a condition here. I mean, this in particular implies that in the inverse limit setting, your modular symbols mod Eisenstein have no p torsion. OK, so that's kind of what's known at this point. I mentioned that there was a fancy way of constructing Epsilon, which is useful. So maybe I'll just, yeah? OK, so yeah. So this one, there's a condition, and you know about this condition. Yeah, this one has to do if p divides some Bernoulli number b1 chi, but p does not divide b1 chi inverse, for instance. That implies that this Hecke algebra is Gorenstein in the chi component, or essentially something close to the chi component. This one, under the assumption that this is Gorenstein, then this somehow S mod IS actually becomes like the Eisenstein ideal mod at square. But anyway, under the this one is essentially under the assumption that this one's Gorenstein. This one is essentially cyclicity, so of the minus part of the class group, the p part of the class group, which is implied by Van der Waals conjecture. OK, so what's the fancy way? It's a much shorter, but maybe less intuitive way of constructing Epsilon. So we have an exact sequence, right? 0 goes to t, goes to t. Just wanted to mention this. T plus goes to t, goes to t minus, because it's a more useful description. So this thing is locally split at, right, GQP split. So because of that, if we look at H2, Z 1 over n, so Galois group of maximal unramified outside n infinity extension of Q, sorry, with t plus t minus 1 coefficients, we can map this, then you might say, well, we don't have an H3, but because it's split, we can use what's called compactly supported cohomology. And I'll describe that in a second. It's defined by some cone from global cohomology to local cohomology. And well, let me describe what these two groups are. This is a connecting homomorphism in some long exact sequence. So this group we have an explicit description of t minus. So this is lambda mod c. There was a 1. I twisted by 1 more, so there's a 2. And this c, if I OK, so the first thing to note is because we have cohomological dimension 2. I have an exact sequence, lambda goes to lambda goes to lambda mod c, and that gives me an isomorphism between this group and H2 mod multiplication by c on the group. OK, the next thing to note is Shapiro's lemma tells me that this thing is isomorphic to the cohomology of this thing, and then I need to take really the prime part, because I've only included prime parts in what I'm doing, mod c. But now c kills this group by the main conjecture, if you like, or actually by Stickelberger type theorem. This thing kills this group, so this thing is actually just, well, this group is y prime, so this is just y prime. So C annihilates Y. OK. So the first group is Y. So you might guess that the second group is supposed to be S mod IS, or T plus. And it is. And that's because Poincare duality gives me a nice description of these compactly supported cohomology groups. And what it says is that this H3 is the dual of H1 of the Tate dual. So H0, sorry. So we take H0, we take the Poincare eigendual of T plus, and we take the Poincare eigendual of that. So dual to QP mod ZP, if you like. But H0 is just fixed things under the Galois group. So this is some awful thing. T plus dual fixed by the Galois group dual. OK? But remember that in the theorem it said that T plus is fixed by the Galois group. So that doesn't do anything. So we just have dual of the dual. So it's just T plus, which was, again, by the theorem, S m mod I, or S prime mod I S prime, if you like. So therefore, we get a map. This boundary gives us a map, which I could call Epsilon, which is from Y prime to S prime mod I S prime. And this map Epsilon is the same map Epsilon that I constructed before. So without going up any tower. I should put this higher, sorry. Hmm?
Will you explain this boundary map?
If you right. Sure, I can explain it. Yeah. So what is compactly supported cohomology? It's defined as some sort of cone. So on cochains. So we have continuous cochains, which define our cohomology groups. And we can take the cone. So CC, the continuous cochains of Z1 over n with coefficients in some A, or A, are going to be the cone from the global cohomology of A to the sum V dividing n, I guess, or L dividing n here, CQL A. And then I shift the whole thing over. So on cohomology, what this automatically gives me by defining this as a cone,
What's happened to P in this? Is P divide n or not?
P divides n everywhere. Yeah. And A is some sort of ZP module and ramified outside n. ZP, yeah. Okay. So automatically from this fact that we have this cone, it's just a construction that gives you long exact sequences in cohomology. So we have, if you like, H1 Z1 over NA goes to direct sum L dividing n, or HI, sorry, Z QLA, and then goes to compactly supported cohomology in 1 degree higher, HI plus 1, QL, A, and then continues. So we have a long exact sequence like this, and it stops at H3 compactly supported because other things have cohomological dimension too. So yeah, P is odd here. And so, right. So now I want to apply this to this sort of sequence. So I need a second object. Yeah, to prove it's a little tricky, but let's see if I can do this. So how would I define? I need some other cone for T1. And I define this thing as the cone Z1 over n T1 goes by the local splitting. So I have a local splitting from T to T plus. And this splitting works for all L. So for all L dividing n, if you like. Actually, all the groups are trivial except for except for L equal P. So when I go to the groups I'm interested in.
So where you wrote in that long exact sequence,
Yeah.
HI plus 1 complex support, the QL should be at Z. 1%, right?
Oh, thank you. Yeah. Yes. Yeah. OK, so I define this cone. And what you can see just by construction of the cones is that I have,
So is that T plus or T?
oh, and then minus. I'm going to use the local splitting. So it goes from T back to T plus. So yeah, all the local splittings. So yeah, right. And so now by construction of these cones, I actually have this thing sitting in an exact sequence of complexes where the compactly supported, so this is just by some diagram of chain complexes, the compactly supported cohomology of T plus is here, T plus 1. And then here I have the usual cohomology of T minus, because I didn't somehow change that, shifted by 1, I guess. Or is it just this? I guess it's just this. Right. I have an exact sequence like this. And then if I take the long exact sequence, then I get connecting homomorphisms to cohomology, compactly supported cohomology. So that's how that goes. Yeah, sure.
Annihilation result is not involved in first construction of epsilon.
No. I guess, let me see, is it? Not that I see. No. But I mean, this is not the main conjecture, right? This is just a weaker Stickelberger type thing.
Do you expect that
Mm-hmm.
the H3F is 0?
Yeah, that's a good question. Yes, because that's saying that the co-kernel of epsilon is
Because
0.
there's another term, yeah.
Yeah, there's no term after that. Yeah. So that's equivalent to the surjectivity of epsilon. Yeah. H2F. Yeah. Good question. No, that's not. I don't think that's 0 in general. So what's interesting is, yeah, you can actually ask what happens from H1 goes to H2 compactly supported. Turns out, and this is part of what Fukai and Kato use in their proof, when you map from H1 to H2 compactly supported, both of these groups are still isomorphic to the same groups. In other words, this group is still y prime, and this group is still S mod IS. This map, however, is plus or minus the derivative xi prime times epsilon. So yeah, so you could have some co-kernel there. Yeah. It's bizarre, but that's a true statement. Actually, I hoped maybe I'll say something about that at some point. But yeah. So anyway, that's another.
You said the H1 to the H2 compact is C prime times epsilon.
Yeah. 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 So I don't know. I was going to prove the theorem on T, in other words, the structure of T, is that, or would you prefer me to say something more about the proof of Foucault-Kato result? Oh, maybe I'll prove the theorem on T. Okay. So, okay. So, so let's take M parts everywhere, and I want to omit them so I don't have to write M everywhere. Parts and omit notation.
So if we prove surjectivity,
Right, you get injectivity. Yeah, that's true. Yeah. Well, it's not quite known that the orders are the same. Because it's cus forms mod I. Yeah. But it's known that, that this has order at least the order of this. So if you have surjectivity, you have injectivity. Yeah.
So what theorem is this?
Oh, yeah, that you have this exact sequence.
Okay.
Yeah. Okay, so we remember I considered T tilde, which was the cohomology of the open curve. So I can consider T tilde mod T. If you like, there's two different ways you can show this as lambda. I already mentioned one, so let me mention if I take plus parts. This is just the quotient on plus parts. The minus parts stay the same. And this is, I'm taking M parts. And this is the modular symbols. So this is a homology relative to the cusps. Mod S. And this thing is isomorphic to lambda, generated by essentially as a lambda module, it's rank 1 lambda module, generated by the class of the path from 0 to infinity as a lambda module. This thing, mod S, is. OK, so this is essentially due to OTA. On the other hand, we have the Monin-Drimfeld type splitting. So that splits over QP the map from T tensor QP into T tilde tensor QP. Let's call it S. And so we can consider the, if you like, the congruence module again, S T tilde mod T. And this thing, just like before, is all coming from the quotient part, actually, and which is the modular forms mod cusp forms by what I said about D of the T quo and T tilde quo. So this thing is, again, lambda mod C. OK, so we have OTA's pairing. T cross T to lambda iota 1 that I defined before. And it's perfect. I can extend it now slightly to this slightly larger group. You see, I just have to add in some denominators. So I could extend this to a map ST tilde, cross T to 1 over lambda iota 1. Now, right. OK, so from that, if you like, I can work mod T here. Then that'll factor through the quotient mod I here. Remember that T was T tilde mod I T tilde. OK, so I have a map. This is generated by the image of 0 infinity. And then I have T here, T mod IT. And then I get a map to, if you like, 1 over c lambda mod lambda iota inverse. It's awful. But I just multiply by c. I get lambda mod c iota 1. And this is still, so if I take, so this thing is part of a basis of, well, this thing does generate this. So, OK. So I could pair with that, and that gives me a map Yeah.
Oh, it's that Roman T is curly T mod I, actually, sorry.
Yeah. Yeah. So that gives me a map, and because actually, I should say that this quotient is fixed by the action of the Galois group. GQ acts trivially here. Here. So because of that, pairing with 0 infinity gives a map T to lambda mod C iota 1. It's surjective of H GQ or lambda GQ modules, H mod I GQ modules. So let's declare this thing to be Q, and let's let the kernel be P. So then automatically, of course, I have an exact sequence now of HGQ modules. 0 goes to P, goes to T, goes to Q, goes to 0. Now, I can consider the
surjectivity, what is it?
Yeah, that's because the pairing is perfect, and sort of 0 infinity is, if you like, it's part of a lambda. Well, I mean, it generates this thing, mod T. Why does it generate this thing mod? Yeah, so that's what I was saying here. Yeah, you can. The entire difference between T tilde and T lies in the plus part. And so actually, OTA, so on the Eisenstein parts I'm looking at, okay, I'm only looking at these Eisenstein parts with these particular characters. On those particular parts, actually in this quotient of homology of the close relative homology mod homology, the only thing that survives is obviously going to come from cusps. It only comes from 0 cusps. The infinity cusps all die. And so this thing is really just generated by the 0 cusps. And so this thing, as a lambda module, so this thing, its boundary is 0 minus infinity. Infinity dies. And so it generates. That's actually because I assumed all these conditions on the characters. So OTA actually explicitly sort of determines various Eisenstein elements, which are the residues of Eisenstein series. And this is some special case of what he does. So another thing to note is that because of, again, the assumptions on character, the sort of non-exceptional, one of the assumptions is essentially that P distinguished, that the representation, the Galois representation, is P distinguished. So there actually exists a splitting here as H modules. And how do you distinguish? Well, the GQP acts trivially on this. And the point is that it acts non-trivially on this. And how do you see that? Well, you can look at, so if I'm looking at some on theta parts, right? So I look at some theta. I could look at theta omega inverse. If this thing is not 1, then can distinguish by the action of so this you can think of as the Galois group of QP mu p over QP, distinguished by action of inertia. So in other words, some element of inertia which restricts to some generator of Galois group of QP mu p over QP acts non-trivially here, but trivially here. So they're in different eigenspaces. And if, on the other hand, this is equal to 1, then we can still look at theta omega inverse of P, which by assumption is now not 1. And so then we can distinguish them by the action of a Frobenius. Frobenius acts trivially. Right. Frobenius mod I, at least. The point is that the Frobenius acts trivially here, but non-trivially there, because the Frobenius acts as UP. Okay. So anyway, there exists a splitting, is the point, and as H modules. And now let me draw a diagram. So we can look at the T quo mod I and T sub mod I, call them T sub and T quo. And now we have obvious maps like this. And the point here is, remember that T sub is just H mod I as an H mod I module. So is this. This thing can't have, so we have a H module splitting here. This thing can't really have any quotient because it would have the wrong action here. So that sort of forces, this forces this is an isomorphism. They're both isomorphic to lambda mod C. So surjectivity gives you an isomorphism. And then because this is an isomorphism, you get this as an isomorphism. And now that you have either one as an isomorphism, note that this is an exact sequence of local modules, and this is an exact sequence of global modules. And so therefore, we have that this sequence is locally split now at P. Okay, just by, you go here and compose with the inverse of the isomorphism, then inject back in. Okay, so we have locally split at P. And the only remaining thing is to see that P is T plus and Q is T minus. And right, so right, I ran out of space.
Sorry, I wasn't following.
Yeah. Oh, Q is this thing, just by definition.
Okay.
Yeah. And P is the kernel if T goes to Q. So I artificially construct a global sequence. And now I want to claim that this global sequence, which I just showed is locally split, is the same as like T plus and T minus here.
Yeah.
So this is the way I've constructed a quotient of T minus, and you want to actually see it's T minus, and not that some part of T minus is here. So the idea is you write T as direct sum T sub plus T quo, and you think of Galois elements as acting as matrices, right, on this. So in other words, we get a representation, if you like, rho bar, which is A bar, B bar, C bar, D bar. And now B bar is 0, okay, because we have it's locally split. Oh, sorry, B bar is 0, and because it's locally split, C bar is 0. And then so AD bar being the determinant is the determinant, which is, as I was mentioning, it's like chi p sigma diamond operator sigma on some element. And but A bar sigma describes the action of sigma on T sub, which we know, right? That's isomorphic to lambda mod C iota I, so which is that action is chi p of sigma diamond operator sigma. So in other words, D bar is 1, and A bar of sigma is the determinant. So, but now rho bar is odd. Forces, right, now D bar is acting on the plus part, right, means that this now forces T quo to be the plus part and T sub to be the minus part. Here I'm using, I guess, maybe I should say T sub is the minus part. Oh, surjects onto the minus part, and t quo, t plus surjects onto t quo. Right, which means, which is exactly what you wanted. Is that? Yes. So this becomes an isomorphism.
So one of them is equal and the other naturally.
Right. Well, this is, yeah, so it's a little tricky, right? We have splittings now, so we can think of everything as sitting inside. This is naturally, we should think of as the quotient of t plus. And that's really t by t plus. And this one, this one's a quotient, this one's a sub, this one's a sub, this one's a quotient, naturally. Okay, so, and that's independent of our choice of decomposition group. I mean, we have split. Okay, so I think I'll just say one thing about the proof of yeah. Since I mentioned it earlier, maybe I'll just no, maybe there's an interesting result here. So this time, I claimed earlier that this thing is y, right? So let me explain why that is. So I explained why H2 gave you y. So H1 you can think of as sitting inside you have a long exact sequence with lambda goes to lambda mod c. And so I have lambda iota 2 here, mod c. And I have H2 z1 over n lambda iota 2 c. OK? So remember that I already said, so this is y, and it's killed by xc. So this thing really is just y. So if I want to show that this thing is y, then I just need to show that this group is 0. But this group somehow is coming from units in some sense. In fact, but because of the twist by 2, it's coming from minus parts of units. And the only minus parts of units that you have are roots of unity. So if you like, what this thing is somehow it's ZP2, and then you take the GQ mu n coinvariance of that, so it's some finite group. But then I have to take, because I'm only looking at prime parts, I have to take prime. But I assume that theta is not omega squared. So this group is 0. So, so this thing becomes isomorphic to y. So it's bizarre that both H1 and H2 are isomorphic to y. But you can exploit this in a very interesting fashion. And Fukaya. Oh yeah. So so somehow if I do Shapiro's lemma here, right? By Shapiro's lemma, this H1 is isomorphic to H1 z mu n 1 over n zp2 prime. And now the point is I can sort of go up the tower and come back down like I did before. And what you see is that because the ZP1 coefficients, I would get units. If by Kummer theory, I would get n units in my group. But yeah. In fact, okay, I should have maybe. Okay, you have to deal with maybe some fact that you could have n units other that aren't just units. But when I go up the tower, the only units that survive then are p units. Anyway, the point is that this prime is in the plus part, right? All the characters are even. So I have a ZP2 twist. So that's like a twist by one of the units at some level above. So that becomes odd parts of the units, and then a twist back by one. Well, what are the odd parts of the units in the inverse limit under norms? They are just roots of unity. So I get a ZP1. And then I twist by one, and I descend again. I get the co-invariance for ZP2. And so this group actually becomes the GQN co-invariance of ZP2. And now, but I've restricted my choice of characters implicit in the definition of lambda, right? So I limit, in particular, I didn't allow theta to be omega squared, mod p, or theta is a prime to p order character. So this group is actually 0 by assumption. Yeah, so that's roughly how you get that this group is 0, and so this just becomes y. And so Fukaya and Kato exploit this. That's maybe useful to leave up. As follows. This is where the derivative appears on one side of their work. So you can look at h1z1 over n t minus. I have t minus, right? I wrote t minus 1. And now we know that this maps isomorphically to y. On the other hand, before I told you that y maps isomorphically to h2 t minus 1. And so now I want to map from h1 to h2. How can I do that? Well, the simplest way to say it is I could take cup product with the p-adic cyclotomic character on the left. So you might ask, what map is this that makes it commute? Right? Both groups are y. Here I take cup product. This is the p-adic cyclotomic character. You can also interpret this as some sort of. The t minus has a 1 in it, right? Because it's the cohomology of the modular curve with a 1.
What do you mean? You're saying if you take the cup product with the t twist.
No, this is in cohomology. This is in h1 z1 over n with trivial coefficients. Yeah. Yeah. So right. So it goes from group to the same group. What is this? This is C prime. So that's where the C prime appears in their, actually, in the order they appear in their work. You have something like var pi here, and then epsilon here. Anyway. Right. So there, yeah. So this C prime appears by this interesting Galois cohomology computation, which uses the fact that the characteristic ideal of y is C, if you like. The other derivative actually appears. Last time you told me that, well, you kind of have an inverse map there already, right? When I had the z sharp and then I had some regulator computation. Well, it's exactly this regulator computation that gives you the other C prime. So when I compose this z sharp map with some regulator mod I get exactly multiplication by C prime. And then you have to compare the two sides to get the equality. So that's roughly what they do. So I spent a lot of time trying to remove the derivative. And in fact, you can remove the derivative from both sides. But somehow, the derivative is, in a sense, what glues the two sides together. In the sense that it's like to remove the derivative, you might try taking a derivative in a different direction. And in some sense, instead of landing at some intermediate level between q and q mu n p to the infinity. But what you have at the level, or q mu n and q mu n p infinity, what you have at the level of q mu n, which is nice, is you have these cup products of Siegel units. You have nice global elements. And that's sort of, in knowing that, the existence of global elements is where is sort of crucial here. I'll just say that. So maybe I'll stop there.